Hey there, and welcome to The Explainer. I am absolutely thrilled to jump into this one with you today, because we are going to be unpacking one of the ultimate cosmic mysteries. We are looking at the exact mathematical breakdown of what actually happens when you cross the threshold of a rotating black hole. Okay, let's dive into this. For decades, basic physics and, well, basically every sci-fi movie ever have taught us that black holes are just dead-end points of infinite density. You fall in, you get completely crushed, and boom, that's the end of the story. But when we look really closely at rotating black holes, which physicists call Kerr black holes, the strict mathematics of general relativity tell a wildly different story. It forces us to ask, what actually lies beyond the center? To understand this, it all comes down to something called the Kerr ring. See, in a rotating black hole, that crushing singularity isn't just a single inescapable dot. The sheer force of the rotation actually stretches the singularity out into a ring shape. And here is the truly mind-blowing part. Because it forms a ring, it leaves a regular, flat, and totally traversable disk right in the middle. It's literally like a cosmic doorway or a completely open window sitting right there at the heart of the black hole.
Now, you might be wondering, is it actually possible for anything to pass through that doorway? Well, the paper we're looking at proves that. Mathematically, yes, it absolutely is. The math confirms that paths of light and matter, which are known as geodesics, can cross right through this central disk in a finite amount of time, completely missing that crushing ring singularity. There's just one specific mathematical condition to make the crossing. A value called their Carter constant, denoted by the letter Q, just has to be less than 0. If Q is negative, you can sail right on through.
So if you can cross it, where exactly does this doorway lead? Let's check out the default answer: a negative mass universe. For a long time, the standard mathematical model has been something known as the Boyer-Lindquist continuation. This model smoothly and perfectly extends the geometry straight across the disk without any weird breaks or hiccups. It creates this beautifully analytic, unbroken path into a second asymptotic region, which, in plain English, is essentially a second universe. But while the math is incredibly elegant and clean, there is a massive physical catch when you start looking at the properties of this second universe. The catch is -m. Yep, negative mass. When physicists use this mathematically perfect model, it calculates that the second universe has a mass of -m. And physicists absolutely hate this, for very good reason. A negative mass universe doesn't make any sense whatsoever in our physical reality. It means the exact same gravity that pulls things together here would violently push them apart over there. So it's mathematically pristine, sure, but physically impossible. Because a negative mass universe is so deeply problematic, we have to look for other solutions. So let's explore 3 alternate realities and see if we can somehow fix this negative mass problem. This brings us to the first alternative proposed to save our physical reality: the one-ended model. Instead of just accepting a bizarre negative mass universe, this model just cuts off that second region entirely, leaving us with a single universe. But there is a huge risk here. If you just truncate the space-time without handling the boundary perfectly, you literally break the paths of light and matter. The geodesics hit this terminal boundary and just stop. They hit a brick wall, basically, meaning the space-time is incomplete. Now, if we want to keep that second universe but force it to have a normal positive mass, we end up with 2 double-sheet models. The first is the same-time model, where we assign positive mass to the second universe and time flows normally. Makes sense, right? But the second option is a truly mind-bending approach, the time-reversed model. To mathematically account for that pesky negative sign while keeping the physical mass positive, this model suggests that in the second universe, time literally flows in reverse. To sum this all up, every single model for what lies beyond the black hole comes with a really severe cosmic trade-off. Boyer-Lindquist gives us perfect math, but an impossible negative mass universe. The one-ended model gives us positive mass, but is geodesically broken. The same-time model gives us 2 normal universes, but the math requires a really rough seam to stitch them together. And the time-reversed model? Well, while it's super creative, it introduces massive global time travel paradoxes. So to really test if those positive mass theories hold any water, the author of this paper conducted a brilliant mathematical experiment, the space-time gluing test, where we attempt to literally stitch these universes together. The author used Darmois-Israel matching data, which is essentially a super advanced mathematical toolkit for joining different spacetimes, to try and glue 2 positive mass universes together right at that central doorway. Now, if you look at the intrinsic geometry of just the disk itself on a constant time slice, it actually looks incredibly cooperative. It's perfectly flat and normal, almost like a simple Euclidean plane. But what's really wild is what happens when we zoom out to the full four-dimensional geometry of spacetime. In 4D, the disk is not flat at all. The mathematical boundary, what physicists call the time-like disk world tube, has a non-zero second fundamental form. Put simply, it doesn't sit flat in spacetime. And as you approach the edges near the X-sized ring, the curvature diverges wildly. It bends and warps completely out of shape. Because of this chaotic bending at the edges, the author delivers a pretty massive bombshell conclusion. I'll read it directly. A literal, normal reflection gluing is not a C1 vacuum matching. In everyday terms, this means you absolutely cannot smoothly stitch two positive mass universes together at this doorway. The math proves that the edges just don't line up. The seam between the universes is way too rough and jagged. Which brings us right to the climax of the explainer, where we have to face the ultimate impasse between mathematics and physics. It's time for the final cosmic verdict, the ultimate trade-off. So the crucial point is how we weigh our two final choices. On one hand, we have the Boyer-Lindquist model. It is mathematically privileged, perfectly smooth, and beautifully elegant, but it requires us to accept an impossible negative mass universe. On the other hand, we have the positive mass alternatives. These are physically motivated and totally realistic for a universe like ours, but they are mathematically messy, requiring a broken, chaotic physical shell right at the threshold of the doorway. And honestly, we have to remember that even if we decide to accept that messy doorway just to keep our physics realistic, any explorer traversing this black hole still has a rough road ahead. They'd have to navigate that distributional surface tensor, which is just that chaotic junction shell we talked about. They'd have to deal with chronology violations, meaning closed loops of time travel. And they'd face mass inflation, which is a terrifying instability caused by intense radiation trapped at the inner horizon. So we are left with a truly monumental question about the fundamental nature of reality itself. Will we choose perfect math with impossible physics, or realistic physics with a chaotic, violent threshold? I want you to truly ponder which reality you believe governs our universe. Thank you so much for hanging out and exploring this incredible paper with me. Keep questioning the cosmos, and I'll see you in the next explainer.